Boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with Dave Ansell. Hello, Dave.
Hello.
So with Kat Arney. Hi, Kat.
Hello.
And I'm, of course, Chris Smith. And in the news this week, scientists have discovered how they can turn stem cells into germ cells, in other words, sperms and eggs, and that could offer hope to people who are affected by infertility. Also, at 1 million frames per second, is this the world's fastest camera? In fact, it's so fast that scientists say they can see individual nerve impulses travelling along nerves, and we'll find out how it works in just a moment. And, with an eye on the 2012 Olympics, scientists have found that people with high heels are actually the fastest runners. But we're not talking stilettos, though, thank God. Kat.
You've never seen me in a pair of heels. Anyway, thanks, Chris. Also this week, it's our science question and answer show. We've got an inbox bulging with your questions, including why you shouldn't defrost and then reheat food too many times, can copper or magnetic bracelets benefit your health, and if hot air rises, why are the tops of mountains so cold? That is a great question, so we'll be answering all of those and more. If you've got a question you'd like to ask us, then do send them in, and we'll give you the details of how to get in touch with us in just a second. Dave.
Thanks, Kat. And in this week's Kitchen Science, I'll be building a homemade helicopter. Well, I'll show you how the rotor works anyway. All you need is a small piece of stiff card. I've been using a bit out of a piece of card out of a Kleenex box, and 3 pencils and some sticky tape.
You always bring some lift to the programme, Dave. It's good to have you here. It is The Naked Scientists, so if you'd like to get in touch with us with a science question or just a comment, just want to say hi, Chris at thenakedscientist.com.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, this week, scientists have made a pretty monumental step forward in the world of stem cell biology, and specifically understanding how the body can make germ cells. Those are sperms and eggs. Now, the way in which human bodies make their germ cells has really been something of a black box. We just don't know what goes on in there, for the simple reason that it's very hard to study. It's very hard to make these cells in the dish, and there's no animal that's quite like a human. So it's very difficult to go and look at a mouse and then extrapolate what goes on in a mouse and assume that the process also works in a human. It's, of course, unethical also to study humans. What we'd really like is a way to make lots of these cells in the dish, and then we could study them and understand the genetics that goes on, because many people are infertile because they can't make the right numbers of germ cells and they can't get the DNA right in their germ cells. Remember that sperms and eggs have half the normal numbers of chromosomes in them, in order so that when they fertilise each other, half plus a half makes the whole. In other words, you get one set of chromosomes plus another set of chromosomes come together and you get the right amount of genetic material. That was the problem, but now scientists might have a solution. This is Renee Rayo-Pera, who's a researcher at Stanford University. She's got a paper with her team in the journal Nature this week. What they've done is to take human embryonic stem cells, so these are the first cells that form after an egg has been fertilised, and by adding various growth factors that people in the past have shown can make cells begin to mature into germ cells, they then were able to define a family of genes which, if you add them to these cells, make them turn into germ cells. And these are genes including one called DAZ, D-A-Z, another one called DAZ-L, D-A-Z-L, and one called BOULE, B-O-U-L-E. And if those genes are added to these developing germ cells, they can up the number of cells that they get out that are like sperm and eggs. They're sort of early sperm and eggs. And why this is important is, A, it will teach us how these cells work, how they actually make the right amount of genetic material, and B, a long way into the future, it means that we might be able to help people who do have a problem with infertility, because it's one mechanism by which we could make artificial cells for them so that they can get the ability to make germ cells back and therefore father or provide an egg to make a baby.
And there's all the sort of coverage of this that says we could do away with men, we could make sperm in a test tube. Is it really going to be possible, do you think, to actually create a baby from eggs and sperm that had entirely been grown in the lab?
I think it is possible, as long as it's safe. And the thing that the researchers showed in this Nature paper was two things. One, that when the cells first were matured, in other words, they first added these growth factors and began to make them into stem cells, the first thing they noticed was that the DNA was wiping the epigenetic slate clean. What I mean by that is that it was removing chemical modifications called methyl groups, which are added to the sides of the DNA, which turn on and off genes in specialised cells. And in order to unspecialise and be like an early embryo, you need to get rid of that. These cells did that. They also counted up how many chromosomes they had in them. There seemed to be, in some of the cells at least, just one set of chromosomes. It's very encouraging, but early days, and they certainly haven't taken some of those cells, mixed them with some other cells and seen if they can actually start embryos going, because I think A, that would be unethical at this stage, and B, it's another step they've got to take.
It's certainly really interesting news. This is the field I used to work in when I worked in a lab, and as well as the sort of the marks on the DNA, there's also lots of marks on the proteins that package the DNA, on these histone proteins, so it'll be really interesting to see how this research progresses.
Now, there are many processes in physics, chemistry and biology, just about everything else, which are very interesting but happen far too quickly for us to be able to see, so they're very difficult to study. Now, there have been many forms of high-speed imaging to look at them, but they tend to work by making conventional cameras faster, which normally involves expensive mechanical systems, and the whole systems cost up to hundreds of thousands of pounds, if not millions of pounds. And quite often, if you get very, very fast, you can only see a very, very few frames. You can only take like 100 frames or something, so you've got to catch exactly the interesting thing, which can be very, very difficult. And because their the exposure time is so short, they get very, very low light sensitivity. So if you're not careful, you have to illuminate the sample so brightly that the light levels will just fry it. And this is useless if you're looking at something biological, because a fried cell isn't going to behave the same as a normal cell. Now, the European Megaframe project have managed to build a camera capable of 1 million frames every second by approaching the problem from a different direction. They've taken sensors called single photon avalanche diodes, which, as the name suggests, can detect individual photons. So this camera is very, very sensitive because it can actually see individual photons rather than 10 or 20 like a normal camera. And these detectors are connected to timers, which can tell you exactly when the photon arrived to within 100 picoseconds, which is like a 10 billionth of a second, so very, very accurately. And then they're ready to receive another photon in about another 32 nanoseconds after that. Now, they've made people have had these for a while, but now they've managed to build arrays of these detectors up to 128 square. Which is a long way from high-definition video, but immensely better than the alternative of using individual detectors. Now, the precise measurement of when each photon gets to the detector means the camera can be used in forms of image which know precisely when the photons arrive. So things like, there are some dyes, things like Oregon Green Bapta-1, which emit light after they've been given energy by a laser, and how fast that light decays is dependent on the concentration of things like calcium. So
what sort of things can you actually use this camera for? I mean, presumably not for taking like pictures of football or something like that.
Well, there have been all sorts of... you could look at anything which happens very, very quickly, but specifically things which emit light, because it's very, very sensitive. So these dyes, if you put them in a cell, like a nerve cell, the amount of calcium is very important to where a nerve cell fires. And so if there's lots of calcium there, then it's going to change the decay rate of this, how quickly the light is emitted from this kind of dye. So you can keep flashing it with a laser with one kind of light and then look at the light coming off it. And if you know exactly when those light photons are coming off, you can actually see a pulse going down one nerve cell. They've actually taken photos of a pulse going down a nerve cell, and they reckon that as they get more pixels in their arrays, they'll be able to see like groups of nerve cells, like 10 or 20, and see how signals pass through groups of nerve cells.
So you could actually look at thoughts travelling around the brain. That would be fantastic.
Or at least a slice of brain.
A small slice of brain. Anyway, from the very, very small to the slightly larger, and talking about building the perfect sprinter. Now, you probably think of someone with long legs and powerful muscles, but new research published in the Journal of Experimental Biology suggests that it's actually the size of an athlete's heels that might be important in giving them the edge.
A bit less sexy then.
Yes.
But how does this work?
Slightly less sexy. This is research by Stephen Piazza and his team in the US. He was approached by an American footballer to find out if he could help him get the edge over the competition. Now, when a sprinter pushes off the ground, their acceleration depends on the leverage they generate by your calf muscles pulling up on the back of your heel, sort of pulling your heel up, pushing your toes down and pushing them into the ground, so you kind of move forwards and up. Now, Piazza figured that the best sprinters should have a long lever, a long distance between the ankle and the back of the heel. But when he actually measured this particular footballer, he measured how far their tendons move, so as a measure of the length of their heels, he got quite a surprising result.
Why?
Well, he actually found that this particular footballer's tendons moved a much shorter than average distance. So he was a bit confused by this, and they measured the tendons of a number of elite sprinters and long jumpers and compared those with the legs of non-sporty people. And they
like
actually,
me.
Yeah, me both. And they found that on average, the distance that the athlete's tendons moved was 25% less than those of non-sporty types, suggesting they actually had shorter heel levers, which, isn't what you might expect.
Indeed, I wonder what's happening with Usain Bolt then, the world's fastest man of the moment. What do you think's going on?
Well, you'd think that having these short heel levers would be a disadvantage, but when he looked into this, Piazza discovered that sprinters compensate for this by contracting their calf muscles comparatively more slowly and much more powerfully. So this is actually similar to a lot of animals that sprint fast. And the scientists also found that sprinters had longer toes. On average, their toes are 1 centimetre longer, meaning that your feet stay in contact with the ground longer as you push off. So although it appears on first glance that heels may not exactly be designed for speed in sprinters, combining it with powerful muscles and long toes could actually generate more power.
So I wonder if we'll get to the stage where sizing people up for your 2012 Olympic team, you're going to start measuring people's feet and saying you shouldn't be a sprinter because you don't have the right physiological makeup. You should go into distance running or something.
Exactly.
Or go for middle distance events.
I have lovely petite feet, so I think I'm never going to make a sprinter, despite my athletic physique.
Gold medal for world's smelliest feet, though.
Oh, stop it.
Okay, back to the science. If you travelled on an aeroplane recently, you've probably been annoyed by all the rules limiting the liquids you can take onto a plane. The problem is there are various liquids can be used to make explosives or even just a fire. And you don't want terrorists getting onto a plane with all these liquids and causing havoc. And they're very, very hard to detect quickly and easily in the security check.
But why is that? Why?
Well, I guess if you look at a liquid, I mean, lots of things like hydrogen peroxide, which look and smell exactly like water, and it's very, very hard to detect what they are without opening all the liquids and then doing a load of chemistry on the actual liquids, which is very slow, and that will increase the length of all the queues to something horrendous. Now, a group in Jülich in Germany think they may have a solution. They've been looking at the frequencies reflected by liquids in the gigahertz to 10 terahertz region of the spectrum, which is the frequency of your mobile phone and upwards. Now, different liquids have different spectra, so you can detect which one's in the bottle. However, these frequencies are very difficult to deal with, and the conventional spectrometers are very slow, or they only just look at one single frequency. Their solution is to use something called a Josephson junction, which is two lumps of superconductor with a little gap, which is non-superconducting in between them. And the relationship between the voltage across the current and across the junction and the current flowing through it changes when you apply gigahertz and terahertz frequencies. So they've been able to shine a variety of different frequencies onto a suspicious liquid, then focus reflections onto the Josephson junction and work out what frequencies were reflected. At the moment, they've distinguished 5 or 6 different liquids, things like water and a variety of different alcohols, which are very similar. But they think there's no reason why it shouldn't work for more different types, and they can take a spectrum in about a second without opening the bottle, so it should be good for testing baggage.
Can I just ask, why do you need this special, very high-frequency radiation? Why can't you just use X-rays for this kind of thing? Why won't they work?
I mean, X-rays do work. I guess it's just looking in as many different parts of the spectrum and finding the optimum one. You can find some information about substances in the X-ray, but I think it tends to be more about the atoms in individual atoms and less about how they're related to one another, whereas gigahertz frequent terahertz is more to do with whole molecules.
So they might let me on with my toothpaste in future, which is good.
If you're lucky.
Let's hope so. So you two boys, okay, were you really into dinosaurs when you were little? I bet you were.
Absolutely.
Yeah.
One of my first memories, I think, is going to the Natural History Museum in London and seeing that enormous brachiosaur in the foyer.
That's fab,
Definitely.
isn't it? Pretty much all small boys and myself as a small girl was very into dinosaurs. But there is disappointing news this week in the journal PLOS ONE for small boys and paleontologists, and generally anyone who's a fan of dinosaurs. Now, according to a study by Mark Goodwin and Jack Horner, it appears that we may have significantly actually overinflated the number of different dinosaur species.
Oh no, why?
Well, it's quite sad, really. But Goodwin and Horner have been looking at dome-headed dinosaurs from North America. These are known as, pachycephalosaurs, and they have heads like bowling balls. And now they've been collecting fossils in an area called Hell Creek in Montana for about 11 years and doing a really detailed analysis of different species of dinosaurs using techniques like CT scanning and analysing their bones. Now, they compared fossils of these pachycephalosaurs with another dome-headed dinosaur found in Montana and a dragon-like skull that was unearthed in South Dakota. This is called Dracorex hogwartsia, yes, named after Harry Potter's school. Now, the scientists think that instead of actually being 3 different species, these dinosaurs are all actually the same species, but they're just at different stages of sexual maturity. And to confirm this, they looked at another 17 dinosaur skulls from North America.
Oh, well, that is quite drastic, isn't it? That says we need a rethink even then.
Yeah, pretty much. It seems that a lot of the confusion's crept in because juvenile dinosaurs can look quite different from grown-ups. Because as dinosaurs grow up and mature, they develop these wonderful head ornaments, horns, domes and spikes, whereas obviously teenage dinosaurs just wear baseball caps. But scientists may have confused these superficial features, the sort of horns and spikes, with more important underlying similarities between fossils and probably missed the fact that they're actually the same species. So really, Horner and Goodwin think that up to maybe a third of all named dinosaur species may actually never have existed. They're just juvenile forms of other species. Now, other scientists have also suggested this is the case. A species called Torosaurus was recently dismissed as just being a young version of another dinosaur, and a number of duck-billed dinosaurs, and also the fantastically named Nanotyrannus, which is thought to be a miniature T-Rex, may actually not be separate species after all, may all be different versions of the same thing. So sadly, for dino fans, these names may be consigned to the taxonomic dustbin.
Not too late for Diathinkysaurus, though. That still exists in people's imaginations. I guess it's going to take the evolution of DNA technology, which is beginning to get in, isn't it? We're beginning to get to the stage where people can begin to recover proteins from fossils and show that they really are the original tissue. And that means there might be more insights into what the different species are, because you can interrogate the samples chemically. Exactly.
At the moment you have to do it all by anatomical features, and obviously fossils aren't always the best preserving all the anatomical features you might want to look at. So if we could do DNA or protein structure analysis, that would really help us to draw much better trees.
Indeed. Thank you, Kat. Now, also in the news this week, 2 international teams of astronomers have described what we can only describe as the most distant object ever discovered. What they've seen is the gamma-ray burst of a star that died when the universe was just 640 million years old. That's less than 5% of its present age. The universe would have been only about 9% of its present size, and that means the light from that star has been going across space, coming towards us for over 13 billion years. And one of the people who managed to see it was Professor Neil Tanvir. He's at the University of Leicester and he's with us now. Hello, Neil.
Yeah, good evening.
Welcome to The Naked Scientist. So tell us, first of all, how did you make this observation?
So these gamma-ray bursts are actually quite tricky to observe because their sort of main characteristic is a short flash of gamma rays, and of course the gamma rays don't penetrate the Earth's atmosphere, so we have to observe them initially with satellites, and the current sort of workhorse satellite doing this stuff is one called SWIFT, a NASA satellite that the UK is partially built part of the satellite, so has an interest in. So SWIFT finds about, on average, 2 gamma-ray bursts every week, and it reports the positions on the sky of these events down to the ground within a matter of seconds or minutes, so that observers on the ground, like myself, can make follow-up observations using a variety of different large ground-based telescopes, and it's by analysing the information that we get from those ground-based telescopes that we ascertain things like the distance, and in this case, of course, found that it was a record breaker.
What actually causes the gamma-ray burst in the first place?
That's a good question. It's something that is still enshrouded in a certain amount of mystery, but we think actually there are a number of different kinds of objects in the universe that can give rise to these sorts of flashes of gamma rays, but in particular, the one that seems to be most frequently seen is due to the collapse of a very massive star. So we have a star that's maybe 20, 30, 40 times the mass of the Sun. At the end of its life, it ceases to create energy in its core, and it can no longer support nuclear reactions, and so the star just collapses under gravity. There's no pressure, radiation pressure to keep it up. Now, that's a reasonably common and fairly well understood process, but it seems that in certain rare situations, instead of just producing a normal supernova, which is what we would expect normally to happen, such a star can also produce an extremely energetic and highly relativistic jet of material that pierces its way out of the star. And if you happen to be sort of lying and looking along the line of sight down the barrel of this jet, as it were, then you see this phenomenon of a gamma ray burst.
Why is it that we've not seen one that's this old before? Because presumably the universe has had stars forming and blowing themselves to pieces and producing gamma ray bursts like this for a long time.
Yeah, the problem really boils down to just rarity. It seems that it's only very exceptional stars that explode in this way, and therefore, even in the whole universe, as I say, Swift sees a good chunk of the universe in a sense as it scans the sky every day. And yet it still only detects in the whole universe a couple a week. So really it just boils down to the fact that we needed to wait a long time until we were lucky enough to spot one at this sort of distance. If we carry on observing and maybe get even more sensitive satellites and scan even more of the sky, then the hope is in the future that we'll find more at this sort of age.
What can you learn from the fact, or what can you infer from the fact that there was a star burning 600 million years after the Big Bang when the universe was created? What's written into that gamma ray burst in terms of the signature and the chemistry that can inform you about the structure of the early universe around that time?
Right, okay. Well, I should say that in this particular instance, gamma ray burst, the initial flash is very bright in the gamma rays, but then the object that we then sort of track with the ground-based telescopes is the sort of fading ember. It's what we call the afterglow of the burst. And in principle, the afterglow can give you a great deal of information about the local chemistry and the conditions at the time and in the vicinity of the burst. And so that's very important. For example, if we find that there is a lot or a certain amount of heavier elements heavier than hydrogen and helium, so for instance oxygen, carbon, iron, all the things that we're familiar with, if we find that those are present at this time, we know those can have only been cooked in the centers of stars, and so it gives a very important clue not just to what's happening there and then, but what must have happened at even earlier times to produce those heavier elements.
Are they there?
So that's the principle, but on the other hand, the problem is that with the GRB afterglows, they come in a sort of great range of different brightnesses. And really, if we're going to find that sort of information from a gamma ray burst afterglow, it needs to be a particularly bright afterglow. And unfortunately, this one wasn't a particularly bright one. I mean, it was fairly bright, but it wasn't bright enough. And we didn't really, at the end of the day, manage. If we'd have been very lucky with the kind of data that we'd got, then it's possible we'd have done it. But with these things, they go off at random times, and so you have to live with whatever telescopes can make the observations at the time. And we made the first observations, in fact, using telescopes in Hawaii, which we sort of triggered from the UK, but conditions weren't great in Hawaii that night, so you see the problem. We obtained enough data to prove that we'd got this record breaker, but we unfortunately didn't manage to get good enough data to sort of take it to the next step to do those sort of refined pieces of analysis.
I see. And just to finish off, Neil, can you tell us, what does this tell us about the structure of the universe at that time? The fact that there was this big star burning at that time, how does this inform our understanding of the early universe?
Well, it tells us there was at least one star, and of course one assumes that there were more, and we hope in the future, by building up statistics of these things, we'll be able to really sort of measure the rate of star formation in the universe, even at those very early times. The other thing it does is it pinpoints the position on the sky, presumably, of its galaxy that hosted this star, so stars forming galaxies. And we'd like to know not only about the properties of stars at this time, but also the properties of galaxies. And so the galaxy is going to be far, far fainter than the gamma ray burst, because gamma ray bursts are stupendously bright, and galaxies only have, a few 100 million stars in them or something like that. So they're much fainter. And but we can now, knowing the position and knowing the distance, we can go away with all the other facilities that we have at our disposal, like the Hubble Space Telescope, and look really hard for the host galaxy. And so that's certainly something that we haven't yet achieved, but we hope to do next year, is to really search very hard and see if we can find this host galaxy, and therefore, for the first time, learn something about the properties of the galaxies which existed at this really early era.
So you've got plenty of work to do yet. You've got the whole sky to survey yet. Thank you very much. That was Neil Tanvir, who's at the University of Leicester, and he was one of the two teams. He was one of the people from the two teams that reported in this week's Nature their observation of the most distant object yet discovered.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
You are listening to The Naked Scientists with Chris Smith, Kat Arney and Dave Ansell. We're taking on your science questions this week, so if there's anything you've ever wanted to ask, you can Twitter us at Naked Scientists, and you can send an email to chris@thenakedscientist.com. Now, Dave, on Kitchen Science this week, you have an assortment of things there. Tell us what people need to be gathering at home if they want to do the experiment later in the show.
OK, later in the show, I'll be building a little model helicopter. And all you need is a piece of cereal packet about 3 inches, so a couple of centimetres wide, and about 3 inches, about 7 or 8 centimetres long, and 2-3 centimetres wide. Just cut it out with a pair of scissors. You want 2 ideally short pencils, like old ones, which you've worn down, worn down a lot, and 1 long one or a pen, and some tape.
Okay.
And that's about it.
Right, so listen later in the show to find out how you can turn 3 pencils, some sticky tape and a piece of cereal packet into a helicopter. We cannot promise it will fly.
Cheers, Kat. Now, Dave, got a question for you. This is from Sarah Rogers, who says she's a 16-year-old chemistry student. Why don't electrons stick to protons? If there's electrons whizzing around the outside of an atom and the protons are the positive bit in the middle, why don't the two just collapse in on each other?
OK, in a very simple sense, they do stick to protons as much as they can do. They're attracted to protons, and so they form atoms. So an atom is essentially an electron stuck to a proton. What you're really asking is why don't they get any closer than they do? And it's all basically to do with the fact that electrons, in fact everything, has wave properties. And the electron's wavelengths are, by the size of an atom, about the similar sort of size to an atom. In fact, that's the reason why atoms are that sort of size, or of the order of the wavelength of an electron. And you can't really compress a wave any smaller than one or a few wavelengths. And so the electron can't get any smaller than that without actually changing its properties entirely. So it can't actually get any closer to the proton in the centre of the nucleus than it does, and so it is stuck as close as it can. You can cause, if at very high pressures, you can cause electrons essentially to react with protons and turn into neutrons, and this is what happens in neutron stars. But a neutron actually isn't stable just lying around in the atmosphere or in a vacuum. It decays in about 14 minutes into an electron, and a proton sort of forms into a hydrogen atom.
Thank you, Dave. Succinctly put. We'll be hearing from Catherine, who's in Bromley shortly. She wants to talk about genes, but before then, Dan is on the line. Hello, Dan.
Hi there.
Welcome to The Naked Scientists. What can we do for you?
I was just wondering, why do car wheels sometimes appear to move backwards when you view them under streetlights sometimes?
I think I've seen it. As you're driving along, the car next to you is accelerating away, and it looks like their wheels are going backwards in the streetlights, illuminating the wheels of the car.
Yeah, that's right.
Yeah, it's actually a stroboscopic effect. If you've been a fan of westerns, if you were a big John Wayne fan and you used to watch those early westerns where the cart would pull away from the scene and the wheels would initially go forwards and then appear to start going backwards. Did you see those?
Yeah, I've seen that before.
Yeah, it's the same phenomenon. In the case of the cart, it's because the camera is taking X number of frames, in other words, pictures, every second. In the case of the car driving down the motorway next to you, it's the street light flashing on and off about 120 times a second, because mains electricity is 60 hertz, so the light goes on and off 60 times a second. So as a result, you're seeing 60 flashes or illuminations of the car wheel per second. Now, if the car is accelerating, if you imagine, say you drew a line on the car wheel, a chalk mark, and you watched that go round, it would go round in a circle. But you only see it in the dark when it's illuminated by the street light. Now, say the street light flashes on, you see the chalk mark pointing straight upwards. Yeah. The light goes off and the wheel turns around a bit. Agree?
Yeah.
Light comes back on, the chalk mark is now in a new position. Agree?
Okay, yeah.
Now, as the car wheel speeds up, the distance that the chalk mark makes it round the wheel will change according to how fast the car's going. Yeah? There will therefore be a speed at which the wheel will go when it doesn't look like it's moving at all, because the chalk mark is starting, going all the way around and finishing before the light comes back on again. Once it speeds up a bit more, the chalk mark will go right the way round and then a bit further. So it will look like the wheel's going faster and faster and faster. Eventually you'll get to a speed where it's actually going right round and back on itself again, so it looks like it's actually gone backwards a bit, because it's doing more than one complete revolution a bit more, so it looks like it's going backwards, and it's because of acceleration. Once it reaches a constant speed, that effect will stop, but it's a stroboscopic. You're seeing flashes of light illuminating the wheel, and your eye sees it, doesn't see it for a fraction of a second, then sees it in the new position, and when the speed is right, it looks like it's going backwards.
That's excellent. Thank you very much.
You're welcome. Thanks for being a Naked Scientist listener. It's great to have you with us.
Cheers, then.
And this is, I think, coming your way, Kat. Catherine is in Bromley. Hello, Catherine. How are you?
Hello, Will. Thank you.
Welcome to the Naked Scientist.
Thank you. I've just got a quick question for clarification, really. It's often discussed on your show about genes being turned on and off for things like genetic engineering. And I've got a picture in my mind of a sort of a big double helix with old-fashioned light switches sticking out the side of it, which I seriously doubt is correct. And I was just wondering what actually happens, or what is actually meant by genes being turned on and off.
That is a great question, and actually your mental image is a fairly good analogy for it. So if you think about, imagine a long string of DNA.
Yeah.
Now, a bit of that will be the actual gene, and genes are basically instructions that tell a cell to make a particular protein. So you have kind of the recipe bit. And then around that, you have sort of instruction bits. So these are regions of DNA that attract proteins that come and sit on them and tell the gene to be on or off. So these are called transcription factors, and they attract the kind of molecular machinery that actually churns through the instructions and tells the cell to make a particular protein. So you have all these different proteins sitting on different bits of the DNA, and some proteins, transcription factors, tell a gene to be switched off, and some transcription factors tell a gene to be switched on. And so really you do have these molecular switches. You also have another aspect of that, and Chris mentioned this a little bit earlier in the show, is that you have kind of things called epigenetic switches as well, and these are things that are over and above what's in the DNA. You get little molecular, almost like post-it notes or tags stuck to the DNA and stuck to the proteins that are wrapped around the DNA that have more information about when a gene should be used. For example, during development, you should turn this gene on for a bit while you're making hands and then turn it off again. Or should this gene be permanently switched off or permanently switched on? So really there's this whole array of little molecular switches that are telling the DNA to be on or off in a particular cell at a particular time.
Wow, very clever, isn't it?
It certainly is.
Can't you also get bits of DNA which are folded up so the chemistry can't get at it? And
Yes.
Proteins can't get
a lot of these sort of epigenetic factors, when a cell's decided that this gene should be permanently off, that gene kind of gets all compressed up and squished up so that the molecular machines can't actually get to it. So we know that genes that are off are really compressed and wrapped up really tightly, whereas genes that are very actively used are much more open, so all the machines can get into there and read the genes.
It's a bit like moving your tin cans to the front of the cupboard where you can reach them easily, and the ones you don't use very often you shove at the back behind loads of things so you can't reach them very easily because you don't use them. I suppose it's the same sort of thing.
And you label them.
Thank you, Kat. And thank you very much, Catherine. Great question. Catherine Wells.
OK, Chris, we've got a question here from Ian Meller for you. He's always taught at an early age that if meat's been frozen and thawed, you shouldn't refreeze it because of food poisoning. But why is this?
Well, the answer is that some bacteria don't actually get to be bad for you because they infect you. They actually put things into the food that are toxins, and the toxins are not broken down by heat. So the bacteria multiplying in the food leads to the accumulation of toxins in the food, which will then make you ill, even though the bacteria may be long gone by reheating the food. So if you keep cooling and warming the food might spend enough time at a certain temperature which encourages the bacteria to grow and put toxins into the food whilst not themselves actually really posing much of a threat. That's one way. Another way is that if you keep on warming up and cooling down food, some bacteria will just end up flourishing, and they'll go from being at very low level in the food, where they're not growing very fast because the temperature is low, to getting to a very high population in the food where that might be an infectious dose. So to catch salmonella, for example, you actually need to eat about 1 million organisms, 10 to the 6 particles of salmonella. that's an infectious dose. Other bacteria infect you at much lower doses. So it really depends on what the pathogen is and what the way in which it makes you sick is. But the bottom line is, if food spends time at higher temperatures, there's a higher chance that bacteria will grow and therefore make you sick. So the best advice is to either cook it and eat it, cool it and eat it, but don't keep reheating it because that could be bad. Now, I've got a question for you, Dave, which I love the question, and I'm really looking forward to hearing the answer. This is from Kai J. Bernard, who says, "My name's Kai J. I'm from Canada, big fan of the show. Got a question for you. In an article I read this week, they said that the coldest spot in our solar system was a crater on the south pole of the moon. Temperature was about minus 238 degrees. I realise this is pretty close to absolute zero, but if absolute zero is the coldest temperature we can achieve, is there a limit to how hot you can make the temperature?"
Okay, temperature is basically a measure of how much energy each particle has got, or each direction the particle can move in. And so you can take pretty much all the energy away from something, and you can't take any more energy away, and so there's a minimum temperature, so there's an absolute zero. But certainly in any normal idea of physics, anything we know for definite, there's no maximum amount of energy you can give particles, so there's no maximum temperature. You can keep on giving them more and more energy, and the temperature will keep on going up.
So in theory, it should be infinite then?
Yeah, pretty much. Probably there could possibly be a maximum temperature. You might find that maximum energy you can give things due to some bizarre bit of quantum mechanics, but as far as we know, we haven't found a solid one yet.
As the temperature goes up, the particles are moving faster, so therefore their mass will increase, will it not?
Yes.
And therefore, presumably, you have to keep putting in an infinite amount of energy to make it get hotter and hotter and hotter, wouldn't you?
Well, I mean, you're always going to need to... I mean, temperature is just a measure of the energy you put into it. So if you add another 6 units of energy, then it's going to get 6 units hotter, whatever. Okay, and I've got another question here for you, Chris, from Steve Junk. Basically, he wants to know whether vaccines can be given together. He knows someone's just received 4 vaccines at once, and can they kind of wear out the immune system and not produce as good a response?
The answer is both yes and no, actually. When you give vaccines to people, what you're aiming to do is get the immune system to respond so that it can recognise that pathogen in future and protect you with antibodies or cells that kill viruses in cells. Now, one way of vaccinating people is what's called live attenuated vaccine. This is where you grow viruses in culture for many generations, and through the effects of mutation, they lose the ability to make you ill, but they nonetheless remain infectious. So with the MMR, measles, mumps and rubella, for example, you put the virus into the person. It doesn't cause severe disease, but what it does do is to display to the immune system the entire repertoire of viral genes, viral proteins. And what that does is it makes a very broad immune response involving making both antibodies and cells that can attack virally infected cells. And that way your body is very powerfully primed to recognise and prevent you from getting that virus in future. The problem is that when you go into that state of infection, what it does is to release large amounts of a signalling hormone called interferon, alpha interferon in fact, and what that does is put all the cells in the body into this antiviral state where the cells are undergoing surveillance. They increase the surface markers they display to the immune system so that they're more likely to get killed if they've got a virus in them. They degrade genetic material that they think might be viral, and they become much harder to infect for viruses. Now that means if you've had one virus that's an attenuated vaccine about a week or two before, your body makes loads of this interferon. If you then come along and then try and infect yourself with another attenuated virus, for instance another vaccine, it won't work very well because it doesn't get into the cells and the body kills it really quick before it has a chance to prime your immune system. So live vaccines, if you don't have them at the same time but you have them all together, is a bad thing to do. Having them all together is fine because the immune system works by discriminating very powerfully between different epitopes that different viruses display anyway, so that's not a problem. For the present situation we're in now, though, people are asking me, what about flu vaccines? Because lots of people have had a seasonal flu vaccine, but then they're also saying, well, now I need to have a swine flu vaccine. Will the fact that I had the seasonal vaccine about 2 weeks ago make a difference for me having the swine flu vaccine now? And the answer is not in that circumstance, no, because the flu vaccine is a killed vaccine. You're just putting in bits of dead virus, shrapnel if you like, which the immune system then learns to recognise. This doesn't trigger the same interferon response, so it doesn't make you feel ghastly in the same way. It doesn't actually prevent you getting infected with other viruses in the same way.
Is this interferon response the reason why I still feel really quite shattered now, 2 weeks after I had the flu?
Yeah, and the reason that flu makes you feel so rotten, despite the fact that the virus is only confined to your respiratory tract, nose and throat, and sometimes lungs if you get a very severe infection, you probably had symptoms that were nonetheless across your whole body: muscle aches and pains, tiredness, very bad headache, temperatures, just feeling ghastly. That's because of these hormones, the interferons that the body produces in response to the infection, which then turn all of your cells into this very antiviral prime state. So exactly right, yeah. And that's why after some vaccines that do provoke lots of interferons to be released, you have a day of feeling a bit rotten. It's not because you're infected, although you might be. It's actually the interferons, it's your body's own hormones that are making you feel like that.
Distilling the best science. The Naked Scientists.
It's The Naked Scientists with Chris, Dave and Kat. And we're taking your science questions. Sam in Hitchin got in touch and said, is the Earth getting heavier due to plant growth on it, with photosynthesis converting energy into mass? And if so, does this affect the Earth's spin? Well, we have actually looked at this in the past, and the answer is actually yes, because E equals mc squared, Einstein's famous equation. E energy equals mass times c, the speed of light, squared. So if you increase the energy in a system, then the mass must also increase. The sun is adding energy to the Earth's system in the form of chemical, which comes in as light and is converted into chemical energy by photosynthesis. Therefore, the Earth is gaining a little bit of weight in the form of the entrapment of that energy as plant chemistry. But compared with the 40,000 tonnes of dust and stuff that rains in on Earth from space every year, it's probably, quite literally, a drop in the ocean. Kat?
And wouldn't we be losing some by heat as well? Kind of losing some of that energy as plants decompose? And...
Well, there's probably a net income event, but there's probably a net influx of energy. It's all in balance because the Earth's temperature isn't going up or down dramatically, a little bit. But I think on the whole, the Earth is gaining a bit of weight in plants in the biosphere because of the energy income from the sun, I would say. Also got a question from Andy in Seattle, and he says, well, it's a comment actually in relation to your dinosaur story, Ken. He says, while I agree that the news about the reduced species of dinosaurs is a disappointment, this news demonstrates that science, particularly that which focuses on the planet's past, is always correcting itself and progressing. One wishes that creationists would be rigorous too. Ooh. Let's join Jesse. Hello, Jesse.
Hello.
Welcome to The Naked Scientists. What can we do for you?
If I have a torch and I put 3 batteries in it, and 2 are fully charged and 1 is fully drained, will the torch still produce light?
I think that very much depends on the chemistry of your batteries. A battery is essentially a chemical reaction which is split into 2 halves, and the only way, and so you've got part half A and half B, and for the whole lot's got to happen to be driven, and the only way that they can happen is by passing electrons through your circuit. And eventually the battery runs out because you've run out of all the chemicals you need for the chemical reaction. Now basically you're saying if we apply a large voltage and carry on pushing electrons through the battery, what's going to happen? That will depend on what other chemical reactions go on to move charge through the electrolyte in the battery. Normally, that's quite often quite inefficient. If you've got something like a lead-acid battery, which is symmetrical, it will just start charging up in the wrong direction. Certainly, a very simple lead-acid battery will, and so it will turn into a battery but pointing in the wrong direction. If you have other chemistries of batteries, it could cause all sorts of havoc, and it will depend on the exact chemistry. It will certainly have a very high resistance. It'll work for a bit, but eventually you're just going to run out of chemistry. It'll either stop or it could do all sorts of strange things to your battery. It's certainly going to damage a rechargeable battery.
Thank you, Dave. Great question. Thank you very much for joining us, Jesse, as well. If you'd like to get in touch with us and you're listening in Second Life, don't forget we beam this programme into Second Life too. You just have to have your conversation with your other Second Life listeners and we will put the questions into the programme. That's exactly what Sharon Wade did in Second Life. Question, does a supernova, in other words, the death of a star, clear out a planetary system completely of everything that used to orbit the star? The answer is yes. It's the death of the star. The star's gravity is what holds things in orbit around it, and if the star blows itself to pieces, then it will completely decimate the material which is in that system, and that will destroy, unfortunately, any planets. Eventually our sun will blow up like a red giant. It won't actually go supernova, I think it's a bit too small, but it will cook us, but it won't blow apart. But there are stars which do blow themselves to pieces, and they could take things with them. Anyway, Kat.
Nasty stuff. Anyway, from the stars to our cells. Now, this week, there are events running all over the country as part of National Pathology Week. This is giving people a chance to look into the work and the lives of pathologists. And on the line now, we have Susie Lishman from the Royal College of Pathologists to tell us more about this. So, hello, Susie.
Good evening.
Thanks for coming on the show. Now, do tell us to start with, what on earth do pathologists do all day? I have this vision that they're all in the lab wearing coats, cutting up dead people. What do pathologists do?
Well, you're quite right there. Research has shown that most people get their information about pathology from the television, watching things like CSI and Silent Witness, and I'm afraid it's just really not like that. There are over 6,000 pathologists and 20,000 scientists working in 18 different pathology specialties, and less than 1% of those people actually work in forensics, the bit you tend to see on TV. So there's no typical day for a pathologist because they all do completely different things. For example, I'm a histopathologist, a member of the largest specialty, and I study disease by examining tissue with the naked eye and under the microscope. And that might be a biopsy, a small piece of tissue that's removed during an operation, anything up to a whole organ like a breast or a kidney or a limb. So I'm then involved in a team deciding the best treatment to offer the patient according to what I can see when I have a look at that tissue. But then other big specialties include haematology, the study of diseases of the blood and the bone marrow, medical microbiology, looking at the diagnosis, management and control of all sorts of infections, and clinical biochemistry, the diagnosis and treatment of disease through analysis of body fluids like blood and urine.
So you're pretty much covering the whole gamut of biology and medicine there with pathology.
That's right. In fact, over 70% of all diagnoses in the NHS involve pathology in some way. And over 700 million tests are done every year in the UK. That's an average of over 14 for every man, woman and child in the country.
Impressive stuff. So tell us about National Pathology Week. What sort of stuff are you focusing on this year? It's the second year, isn't it?
Yes, last year we just had a general year and we said pathologists and scientists get out there and promote what you're doing. We thought to give it a slightly different angle this year. We've chosen the theme of the heart, and our strapline is Pathology, the Heart of Modern Healthcare. So we're focusing on the diagnosis and treatment of all different types of heart disease by members of all the different pathology specialties.
So what sort of things do pathologists find out about heart disease? What sort of things would you be looking at if someone comes to you with heart problems?
Well, pathologists are involved in even preventing heart disease developing in the first place, which is a very important role. So, for example, diagnosing and treating diseases like diabetes, keeping the blood sugar under control, checking people's cholesterol level to making sure that that doesn't build up, because cholesterol is a risk factor for developing heart disease. And also genetics. Geneticists are also pathologists, and they can look at inherited diseases and enable people to be treated for heart disease before they even know they've got it.
Fantastic stuff. So tell us about some of the heart-based events that you've got going on.
We've got an awareness day at the Royal College on Monday called Think Heart, Save a Baby's Life. And what we're trying to do is raise awareness of some of the heart pathology that can present in the first week of a baby's life, so that parents, midwives and GPs can be aware of what to look out for, because a lot of these disorders, although very serious, can be cured if they're picked up quickly enough. There are also events around risk factors. People have the opportunity to learn about some of the risk factors for heart disease, like high cholesterol, which I've mentioned, high blood pressure, poor diet, and do some interactive events to try and find out what their risk factors are.
And I understand you're also having the anatomy of a heart attack. I was looking at a heart attack.
I'm particularly looking forward to this one. It's at the Royal Institution, and I grew up watching their Christmas lectures, so it's going to be a real treat to organise an event in there. Yes, we're going to have a virtual autopsy with a model who's going to play the body, and we have a pathologist, Ali Winstanley, who's going to come in and talk us through an autopsy and what we would do to what we would look for in somebody who's died of a suspected heart attack. Ali's then going to dissect a pig's heart. For obvious reasons, we can't dissect a human one, just to show a bit of the anatomy and what it is pathologists would look for at an autopsy. And then we've got illustrations of what a diseased heart would look like, so you can see the damage that is done.
That sounds absolutely fascinating. How can people find out about all these events and where to go?
We have a website, www.nationalpathologyweek.org, and that has a full programme. We have over 420 events taking place around the country in schools, hospitals, shopping centres, libraries, absolutely everywhere. So do have a look. They're arranged by region, so there should be something near you.
Absolutely fantastic. Thank you very much. That's Susie Lishman from the Royal College of Pathologists.
Thank you, Kat. You're listening to The Naked Scientist with Dr. Chris, Dr. Dave and with Dr. Kat. It's our question and answer phone-in show. If you'd like to get in touch and ask us any questions about science, you can email us, chris@thenakedscientist.com. You can Twitter at us even. It's @nakedscientist if you'd like to do that. Now, we've got a very interesting question here from Aaron, who's on the phone. Hello, Aaron.
I love your show. Listen every week.
Well, that's fantastic. Checks in the post, mate. What can we do for you?
2 questions. The first one is, why is it that the sun warms us up on Earth while it remains cold above us, despite the fact that above us is really closer to the sun? And at some point closer to the sun, it's probably really hot. So at what point does it become freezing cold?
Okay. Well, it's interesting you should ask that, because I actually got, as well as your email, an email from Chanel who says, if hot air rises, why are mountaintops so cold? And similar to that, Michael Perry wrote to us from Northwich saying, why does a gas get colder when it expands? So between us, Dave, I reckon we can probably wrap this up. So why don't you answer Aaron's question, and in the process, well, why don't I start and I answer Michael Perry's question, which is, why does a gas get colder when it expands? And then you can build on that, because if you think about this, if you have a gas which is, say, in an aerosol. So it's the container you're going to spray into your armpit with your deodorant. There's a gas under pressure in there. When you spray it in your armpit, it feels very, very cold. What's happened? Well, the gas has expanded. Thought about simply, if you imagine there's some kind of piston inside the aerosol can, when the gas is expanded, it's effectively pushed on the piston. It's done some work, let's say. If something does some work, it must have less energy after it's done the work than before it did the work. Since temperature is proportional to the energy in the particles, if something's got less energy, it's therefore got a lower temperature, so the temperature must fall, and that's why we think that when a gas expands, the temperature goes down.
Okay, and now this is actually very related to why mountains are cold. And the temperature that things are on Earth is sort of a balance between the amount of heat which it's getting either from the sun or from heat moving around the world, and the amount of heat it can lose by radiating into space. We're all radiating. Anything at room temperature is radiating heat in the infrared really quite well. And basically the only things which can absorb sunlight very well tend to be at the ground. The atmosphere is transparent, so all the heat is going into the ground and heating it up. And then that heats up the air above it. And now the tops of mountains are very, very small, so you're basically talking about what's the temperature of the atmosphere at 30,000 feet, 10,000 metres or 9,000 metres. And the reason why that's very cold is because if you have a packet of air which has been warmed up on the surface of the Earth and then it lifts up by convection, or it's moved upwards, the pressure drops to about half the pressure it was before, which means that gas expands, and as the gases expand, they get cold. So the air gets very, very cold. So the air around the mountain is very, very cold. And also, anything which is pointy like a mountain has got lots, can emit infrared light in lots of more directions than a flat thing. It's got more surface area compared to the amount of sunlight which hits it. So it cools down better during the night and emits light into the space very, very much better. So it tends to be very cold.
Thank you very much, Dave. I hope that answers your question, Aaron, and thanks very much for your kind words.
Thank you very much. But why are valleys then often colder than areas which are higher up?
Okay, there's a secondary effect. As ever, the world is far more complicated than you'd like to think. That tends to be because cold air falls. So the valleys, low places on average are warmer, but if you've got somewhere which is high up and the air can cool down on the tops of mountains, it's then denser than the air around it and it falls downwards. And if it's not falling very far, it doesn't compress very much, it doesn't get very much hotter. So you get locally very cold areas in the bottoms of valleys, but globally it's warmer low down and colder high up.
Brilliant. Thank you, Dave. Joanne got in touch from Braintree. She said, found the programme very interesting so far. Thank you also to Susie. She said, thought the bit about the heart was great. We've also got a question from Alan in Waterbeach who says, why can you see the moon during the day? Well, why shouldn't you be able to see the moon during the day? The moon is orbiting around the Earth. It takes the moon about 28 days to go right the way around the Earth, come back to where it started. The Earth turns. Obviously does a complete revolution in one day, 24 hours, and so you would expect to see the moon go across the sky every day, pretty much, at some point. It may not be visible on some occasions so much, but it should be there, so that's not so unusual. Got a question for you, Kat, which is from William, who says, why do magnets have healing properties, if they do?
The answer is they don't. It's basically good old-fashioned quackery, as far as we know. There's this idea that if you wear copper bracelets or magnetic bracelets in some way, it can help with things like arthritis. Research has shown that this is absolute bunkum, that there isn't really any truth in it. There's some recent results published in October where they did a rigorously controlled trial looking at magnetic or copper bracelets compared to plastic bracelets. So people didn't know what they had, and really they found it was just a placebo effect. If you tell someone they've got a magnetic bracelet, they think it's doing them some good, but actually there's no science supporting it. But it's a multi-million-pound industry, so, maybe worth it.
So don't
if
bother
you're making
buying
them.
a copper bracelet or a magnetic bracelet. It just doesn't work. Thank you, Kat. Right, in a minute, we'll be catching up with Dave's Kitchen Science. If you want to have a go at this, you need to grab yourself 3 pencils, some sticky tape and some stiff card. He's cut a chunk out of the bottom of one of those sort of throwaway tissue type cardboard boxes. That's what you'll need. Mark in Bletchley, has twittered us to say he's standing by ready, Dave. He's not sure about launching helicopters off the 17th floor of a building, but he's going to give it a go.
Bringing the facts to bear. The Naked Scientists.
And this is The Naked Scientists with Chris Smith, Kat Arney and Dave Ansell. Got a question from Les in Catfield who says, does water weigh less when it's boiled? My kettle feels lighter when the water's boiled than when it's cold. Well, Les, if your kettle is open at the top, then it would have evaporated a bit of water, so it may have lost weight purely through evaporation. But if the kettle's a sealed unit, then E equals mc squared says if you add energy to the kettle when it's hot, therefore it should weigh slightly more when the water's hot than when the water's cold. Also, Michael in Newmarket says light from a star travels millions of miles away, but is this a continuous beam? Also, if you were in example in Australia, would you see the same light as someone who's in the UK? What do you think, Dave?
You won't see the same photons of light, the individual particles of light, but the properties on either side of the Earth are going to be very, very similar.
OK, so from the stars to helicopters, it's time for our kitchen science. Now, Dave, what have we got here? We've got a piece of cardboard that's about 3 centimetres by 10 centimetres, a rectangle. You've got 3 pencils, 1 long pencil, 2 short pencils about 2-3 inches long, and a roll of sellotape. How do we make a helicopter, and will it fly me?
OK, probably won't fly you, I'm afraid. We'll have to work on that one. But first thing I'm going to do is build the launcher.
OK.
And I'm going to tape the 3 pencils together.
I'm going to give you a hand here. OK, so we're holding the pencil. So there's the long pencil in the middle and the 2 short pencils either side of it. But they're arranged so that they're kind of... the points of these pencils are poking up.
So, so the 2 short ones are either side of the long one and sticking
they're all
out
flat.
the top.
They're flat in a row.
Okay.
So you've got a point, then the middle pencil not sticking up, and then another point sticking up. We're taping them nice and flat.
OK, so we now have... that's our launcher. We now need to make the helicopter.
OK. It's not going to take my weight, is it?
I've already cut the piece of paper.
No comment.
Cut the piece of card. What we want to do is mark... you want the launcher to be in the middle, so point the 2 pencils so it's right about in the middle and along. And the 3 of them
so
are
we're
along
making
the line.
2 marks along the sort of the lengthways in the middle of that strip of card.
And I'm going to punch 2 holes with another pencil or
Punch
a
2
pen or
holes.
something.
So you've got 2 points, 2 holes in the middle of the card that match up with the points on your launcher of the pencils on the launcher.
Now if this is just a flat piece of card, that won't work.
Flat piece of card stuck on the points.
Give it a little bit of lift. So I'm going to sort of fold down a flap on sort of starting at one corner, going down to the middle.
OK, so a triangular flap from the little edge kind of going into the middle.
And then on the opposite corner,
OK.
pushing down in the same way. So now we've got 2 flaps.
So this looks a bit like a sycamore leaf or something like that, one of those flying leaves.
Very similar idea, because now if you take that...
OK, so we've stuck the card on the points of the pencils, the launcher.
And now you want to spin it so you're moving, so the 2 folded down flaps
so they're going to go forwards.
So they're going. So it's going. So they're at the back, and you spin it so they're at the back and spin really nice and fast.
Right. So I'm holding the big pencil between my flat hands. I'm going to spin it like this. Woo! Ooh!
Wow, it's gone in my tea. It really has. It really has gone in my tea.
So my helicopter has landed. That's worth it.
Here's another one I made earlier.
Woo!
That's fantastic. Nearly hit the ceiling. Do you want your rather tea-soaked propeller? It's really good, actually. That's pretty fantastic. What's going on?
OK, if you imagine this flat piece of card with 2 little tabs at the back, pointing downwards, as it spins round, it sort of pulls the tabs through the air. And the tabs bash into the air, and because the tab is sort of curved back downwards, the air gets pushed downwards by the tab. And as Isaac Newton worked out, every action has an equal opposite reaction, so if you push something, it pushes you back. So if the helicopter's pushing the air downwards, the air's going to push the helicopter upwards, and it flies.
So this is the principle of big helicopters that can carry me.
That's right. Big helicopters have a problem, though, because if they're sitting on the ground, if they're spinning this rotor blade round and round and round, that means they're twisting it one way, and every action has an equal reaction, so the
your helicopter's going the other way.
The other way.
But that doesn't happen, so how do helicopters do that?
Normal helicopters either have 2 big rotors, like a Chinook, or they have a little rotor at the back, which pushes them round and stops them spinning round. But there is someone in America who's come up with a cunning plan, which means that helicopters are really expensive and complicated, and the hub which connects the blades onto the helicopter is incredibly complicated and falls apart occasionally, and it's got to be beautifully maintained, otherwise lots of people die. So there's a guy who's come up with a wonderful strategy whereby you basically just get if you have a helicopter and just pull it through the air using a normal propeller, then it will spin round and you get lift, and you can fly very, very slowly, but you can't go up and down vertically. His plan is you get a helicopter blade with two big weights on the end, a bit like this, actually.
Okay.
And then you sit on the ground and you spin it up going really, really fast. And because you're sitting on the ground, you don't spin round. Okay. Because you can't spin the world. The world doesn't spin very fast. And so you get it spinning really, really fast.
It's generating lift.
And it's generate lots and lots of lift. And then you use it to jump up into the air. And then you put the propeller on full power forwards and you get going fast enough before it runs out of spin.
And off you go.
Fly off.
So your own personal little helicopter. That's what I want. So we've got this little cardboard thing here. If people want to make their own miniature cardboard helicopter at home, have we got the instructions on the website?
Yeah, the instructions will be on www.thenakedscientist.com/kitchen science.
So you can see exactly what we've tried to describe on air and build your own little helicopters. Tell us how they work. How far could you make one fly?
Absolutely fantastic. Thank you, guys. Loved it how it landed in the tea. Don't know how you planned that, Dave, but terrific. Right, well, look, here's a question I don't think you under any circumstances will be able to answer. Stefan's on the phone from Geneva in Switzerland.
Hello, Naked Scientist.
Welcome to the Naked Scientist. So what do you want to know?
Well, I would like to know where socks go when I put them into the washing machine. I made the observation that I put matching socks into the washing machine and I get only single socks back. As socks are no quantum mechanical entities, where are the socks going?
I think that you have to give up some socks as a sacrifice to the god of washing. I don't know, maybe they didn't end up as pairs in the washing machine when you put them in.
I've got a theory on this, actually. I think that what happens is that socks very often glue themselves to the inside of the machine. So you remove the washing, but you might leave one glued to the top, so it gets separated from its counterpart. You then go to the washing, hang the washing up, process it, put it all back in your bedroom, all ironed and stuff, and now you've got an odd sock. You find the other one, and then that gets processed separately, but by then you've got this odd sock in your bedroom and you think, oh, I must have forgotten to wash this one, so I'll put it back in the wash. Its counterpart is probably already in the wash. Then the other one comes back from the wash, having been found later, but by then its counterpart is now in the wash and they two remain separate forever. I think that's what it is.
Yeah, there's the same circulating odd socks.
Who knows? I've got plenty of them, I tell you.
I once put a white sock in a washing machine and it came out bright red, so I assumed that I then had a pair of socks with one white and one red.
And actually, we've just heard from Drew Marchant, who sent us an email, and he says, I had to take apart my washing machine recently and I found 3 socks stuck in the drain tube, so this is where I think they end up. That or out to sea. But what's your theory? If you've got an idea as to where these odd socks go, where these 3-legged men come from, then do give us a shout. Chris@thenakedscientist.com, where you can Twitter at us, of course. It's Naked Scientist is our Twitter name. Well, it's that part of the show where we now welcome Diana O'Carroll to come and join us for this week's Question of the Week. Diana, hello.
Hello. Yes, well, this week I've been mostly hanging from the ceiling, that sounds right, to get the best signal.
Hi, I'm Andrew Hawthorne from Fayetteville, Arkansas, and my question is, why does television signal improve when you hold the aerial?
So, should we make television aerials out of people?
Hi, I'm Phil Clark from the Particle Physics Group at the University of Edinburgh. And essentially, when you grab the aerial, you're effectively increasing the size of the aerial, and in particular, your body's full of conducting electrolytes. And a good example of this would be in a laboratory if you have an oscilloscope and you look at the pickup from the mains frequency, you can see a 50 hertz signal that's just a pickup from the resonant circuits in the room. And if you hold the probe in your hand, the amplitude of the pickup increases dramatically. And the same thing happens effectively when you grab the TV aerial. You're improving the pickup that it's then using you to resonate within the circuit to produce the signal in the television. And the TV has to be tuned quite closely to the right frequency, but when you touch the aerial, you will improve the signal dramatically. So the other thing is when you grab onto the aerial, the connectivities between your fingers and the aerial, and the tighter you squeeze onto the aerial, or if your fingers are wet, then the conductivity between you and the aerial will be improved. So it often depends on how hard you squeeze the aerial.
And what about the difference between analog TV signals and digital?
The digital signal effectively is a sequence of on and off bits that come down the aerial, and effectively it'll either be receiving those or it won't. And you may, with the aerial, be able to increase the chances of it picking up the 0 1s correctly, but you'd have to get it all right for it to work. This is also why you need quite a good signal for digital antennas to work correctly.
So, by touching an aerial, you're essentially becoming part of the aerial itself, a big human-shaped TV aerial. Unfortunately, it doesn't work as well for digital signals since they are transmitted in bits, and if one bit isn't picked up by your body, there simply won't be enough information for the TV to display a picture.
On the forum, we had another point added by Graham D, who said that if an aerial is set up correctly and pointing in the right direction, then touching it should actually make the signal worse, because the aerials are specifically designed to pick up certain frequencies, whilst your body might actually pick up a whole range of them, and that would mess up the picture.
Right. Well, that's it for picking up signals, but what about making a deposit?
Hi, it's Harvin Tupol from Milford Haven here. My question this week is, how many children does the average sperm donor create?
Yes, how many offspring do sperm donors generate? If you know the answer, then get in touch. You can email us. The address is chris@thenakedscientist.com, or you can write some lovely statistics on our forum. It's thenakedscientist.com/forum.
Thank you, Dinah. And your timing's actually perfect for that question, because next week we're actually going to be exploring the science of fertility and infertility and what science can do, thankfully, to help people who find themselves in the unfortunate position of not being able to have children. So if you've got any points to raise or questions you'd like to ask about that subject or any aspect of science, then do drop us a line. The email address is chris@thenakedscientist.com. In the meantime, thank you very much to our wonderful production team, Ben Valsler, Mira Senthalingham and Diana O'Carroll. Our presenters this evening, Dave Ansell and Kat Arney. I'm Chris Smith, and until next time, goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.